If we're talking about verifiable built leverage, there's no better starting point than James Dyson's. The sheer volume of his physical iteration is just staggering.
It's a story that's become almost like a myth, right? But you're saying we need to zoom in on the specific engineering lessons.
Exactly. It's not just about the moral of never give up. We
Yeah.
need to look at the method. So the story starts in 1978, Wiltshire, England. Dyson isn't trying to build a billion-dollar empire.
No, he's just annoyed.
He's just annoyed. He's solving a very specific, predictable engineering failure in his own house. His vacuum cleaner keeps losing suction.
Oh, it's the most universal frustration. You hear that motor roaring away, but the dust just sits there.
Exactly. But Dyson, being an engineer, didn't just go buy a new one. He did the engineer thing. He took it apart.
He dissected it.
And the culprit, as he found out, was the bag. The source notes make it really clear that the fine dust, the stuff you actually want to capture, was clogging the microscopic pores of the paper bag.
And that just strangles the airflow.
Completely. It turns a powerful machine into this loud, expensive thing that just pushes dust bunnies around.
So that's the trigger. The engineering process starts with a mechanical observation, not, a marketing focus group.
Not at all. And the solution, the start for it, came from a really unlikely place. He visited a local sawmill.
A sawmill.
A sawmill. And he watched how they were using this huge industrial cyclone technology, basically a giant centrifuge, to separate sawdust right out of the air before it even hit their filtration systems.
So that's the moment of hypothesis. It's grounded in a real-world mechanism that already works, just at a different scale.
Exactly. So the question for him becomes, okay, how do I bridge the gap between this massive industrial machine and a consumer appliance that fits in a closet?
And that is where the real work begins, the hard skill.
That's it. He didn't go write a business plan. He didn't make a pitch deck. He went and built something crude, a cardboard cyclone prototype that he taped to his vacuum cleaner.
It must have looked ridiculous.
Oh, I'm sure it was ugly as sin, but it worked. It worked just well enough to prove that the underlying physical principle was sound. You could use centrifugal force to separate dust before it gets to the filter. And that's the key transition point, where the soft skills have to just step aside for the rigor of physical reality.
Okay, so people hear the number 5,127 prototypes, and they immediately jump to perseverance.
Always. It's become this shorthand for just keep going.
But you make a really critical distinction in the sources. You separate that sort of romantic idea of perseverance from the methodical reality of the iteration loop. What was the actual method behind that incredible number?
This is the absolute core lesson of the Dyson story: method and discipline. Each one of those 5,127 attempts wasn't just another try where he was hoping for a miracle. It was a specific, testable, isolated experiment designed to learn something new about the physical constraints of his design.
So give me an example. What would one batch of prototypes be tested?
Okay, so prototypes 1 through, say, 50 might have focused only on the internal geometry of the cone, just trying to optimize the air velocity. Then maybe prototypes 51 through 150 were all about finding different seals and materials to stop the inevitable fine dust leaks that would undermine the whole system.
So he wasn't just working hard for 5 years. He was running 5 years of successive, highly specific failure analysis.
Precisely. The whole goal was to isolate cause and effect. Did this tiny change in the duct shape reduce turbulence without needing a more powerful motor? Did this new plastic compound resist the stress from high-speed dust particles?
And the only judge that mattered wasn't a focus group or a VC.
The only judge that mattered was reality. Did the device maintain suction or did it clog? That's it. It's a binary outcome. The physics of dust separation was the only thing he cared about.
I think the real leverage point for the listener here is realizing that when you solve one huge problem like consistent suction, you instantly create 3 new problems.
Oh, absolutely. Manufacturability, durability, cost.
You have to build, test, and measure your way out of that whole problem stack. And that's what accounts for the sheer volume of work.
And while he's fighting this war with physics in his lab, he's also fighting a completely different battle with market reality.
Right. This is where the engineering hard skill has to overcome an established business model.
It's a textbook case of disruption.
So explain that market constraint he was facing. What was the problem?
It was the razor and blade model, pure and simple. The big established vacuum manufacturers made most of their profit not from selling you the expensive machine once,
But from selling you the cheap consumable replacement bags endlessly.
endlessly. It was this perfect, high-margin, recurring revenue stream. So Dyson's bagless design was, an existential threat to their entire profit engine.
So when he takes his working prototype to these big companies, they don't reject it because it's a bad product.
Not at all. They reject it because it's inconvenient. It forces them to destroy their most profitable business line.
The source material puts this so clearly. It says incumbents don't reject you because you're wrong. They reject you because you've created a superior alternative that forces them to cannibalize their own revenue.
And that's why the hard skill, the undeniable, repeatable performance of the artifact he built was the only weapon he had. He couldn't persuade them, so he had to build a superior mousetrap that just made their business model obsolete.
Which leads us to the hinge moment. Since the UK market was basically closed to him, he had to look elsewhere.
Right, and his first commercial success wasn't in Britain. It was in Japan.
The G-Force vacuum.
That's the one. He licensed it to a Japanese company, and they sold it for something like $2,000. It became this high-tech status symbol, and it won the 1991 International Design Fair Prize.
And that success provided the crucial element.
Capital. The royalties from Japan were the financial leverage he needed to finally stop licensing his technology to other people, set up Dyson Ltd., and launch the DC-01 in 1993 on his own terms.
So that capital let him control the entire process, making sure the hard-won engineering consistency wasn't, compromised by a partner cutting corners.
Exactly. 5 years of iteration resulted in an artifact that created capital, which then funded independent scale.
The key principle here, based on his brutal journey, this seems absolute.
It is. Hard skills help you survive the build and secure your independence. Never chase confidence. That's cheap. It arrives early. Chase repeatable, measurable results. Those are earned through painful iterations.
And for the listener, this means translating that abstract goal you have, a new feature, a new report, a new sales script, into a physical, testable prototype.
Right.
So what are the specific tactics for this? How do you apply this discipline methodology?
Okay, first, we have to internalize this role. Turn your goal into the smallest possible prototype that proves the core claim. If you claim your new code can reduce latency by 15%, the prototype isn't the full, beautiful user interface.
No, it's a backend script that can just prove the performance claim.
Exactly. Ugly is fine. Ugly is acceptable. But working is the requirement.
And the distinction between the engineer and, let's say, the hobbyist is what you call the one variable rule.
Yes. Run the one variable rule per iteration. This methodology forces you to separate correlation from causation. If you change 5 things at once, the color, the headline, the price, the audience, and sales go up.
You have no idea why. You've learned nothing.
You've learned absolutely nothing. So just like Dyson changing only the duck shape, you change only one element at a time. This isolates cause and effect, and it turns failure from, a personal judgment into specific attributable data.
That is a critical shift in mindset. You're not judging your effort. You're judging the data that the attempt created.
Which brings us to the third tactic, which is absolutely necessary. Keep a meticulous build log. For every single attempt, even the tiny ones, you have to track precisely what changed, what you expected to happen, and what actually happened.
The build log is what separates just repeating something from genuine learning.
It's your history of constraints and solutions. It's the proof of work.
Okay, but let's talk about the big risk here. Dyson spent 5 years. How does a listener avoid that trap? When do you know you have enough hard skill proof to stop building and start scaling, even if the thing isn't perfect?
That's a fantastic challenge to the process. And the answer is really tied to the concept of the minimal viable product, the MVP, coupled with real market feedback. Dyson was ultimately forced to scale when a market, in his case, Japan, validated his working artifact with actual cash.
So the goal isn't perfection.
The goal isn't perfection. It's reliable functionality that proves your central hypothesis. If your key metric is 90% achieved and a paying customer base validates it, the hard skill has been demonstrated. The time to stop building and start selling is when the hard reality of the market gives you leverage, not when your internal team gives you applause.
That's the distinction. The market validation is the ultimate metric.
Yep.
Okay, so for our listeners, here is the micro-step challenge for this section.
All right, pick one hard skill you're developing right now. It could be Python scripting, video editing, building a financial model, whatever.
Okay.
Dedicate 60 minutes today to building a proof prototype. Make it work, even if it looks horrible. Then commit to 5 more iterations over the next 5 days, tracking your changes in a build log and measuring your progress by one specific quantifiable metric.
Like time saved, or error rate reduced, or performance speed.
Exactly. Ideas get applause. Prototypes, backed by data, get leverage.
That sets a really high bar for physical artifacts. So let's transition. Let's move into section 2, shifting from prototyping physical objects to prototyping decisions using rigorous measurement and data.
Right. We're moving from the garage to the strategic use of measurement.
This is where the power of the scientific method applies directly to business. And we start with the case study of Capital One, specifically Richard Fairbank and Nigel Morris back in the late 1980s.
And you have to understand the context. At that time, most banks treated data like historical confirmation. They used it to reassure themselves that past decisions were good ones.
They wanted to look in the mirror. Fairbank and Morris, they wanted to look through a telescope.
That's a perfect way to put it. Their entire approach was built around something they called an information-based strategy. It was about fusing marketing, credit risk, and IT into a single, cohesive decision-making machine.
They weren't interested in data as just an asset to have. They wanted it to be a predictive instrument.
Exactly. They were asking, what specific action, what product design, what price, what offer does the data suggest will optimize our outcome?
So they stopped asking, is this the best campaign idea?
And they started asking, what does the experiment say happens next?
That focus shift must have been huge. It means replacing those high-status conference room debates, which are usually based on gut feelings,
with disciplined experimentation. They began applying rigorous A/B tests, multivariate testing, to explore which precise offer worked for which narrow customer segment, at which exact price point, and under which specific risk profile.
So they had to convince a traditional bank, Signet Bank, to even let them try this. That happened in 1988. What was the pivotal proof point? What validated their entire methodology?
It was the targeted balance transfer offer in the early 1990s. They had a hypothesis that specific segments of consumers were, underserved or just unhappy with their existing high-interest credit card debt.
So they designed a targeted offer, lower rates for balance transfers.
And the response was massive and profitable. But crucially, they didn't treat this success as just a lucky win. They treated it as the organizational mandate to adopt this entire methodology as their only way of doing business.
So the insight isn't just the idea of a balance transfer, it's the institutionalization of the hard skill of experimentation.
That's everything. It required robust operational systems to segment, track, and analyze results at high speed. And the scale they achieved, that's the defining characteristic of this hard skill stack. Published case studies show Capital One running upwards of 50,000 statistically designed tests in a single year.
50,000? That's not just minor tweaks.
No, these were tests exploring entirely new credit products, new offer structures, new risk models.
50,000 tests in a year. That necessitates just extreme discipline. This isn't a couple of data scientists on a side project.
No, this requires the entire organization, from IT to marketing to compliance, to be structured around the scientific method.
It's the very definition of organizational leverage through hard skills. Soft skills, they help you persuade stakeholders to try an idea once.
Right. But hard skills, statistical thinking, experimental design, operational rigor, they make you correct thousands of times. When you can measure and experiment at that scale, you stop having arguments. You just start running controlled tests.
Okay, but let's challenge that scale with its opposite, the challenge of small samples.
Right.
Not everyone has 50,000 customers or the capital for these huge tests, which brings us to the fascinating case of William Seeley Gossett, a brewer.
A brewer at Guinness in Dublin around 1900. And Gossett's situation was the complete antithesis of Capital One's later scale. His job was to maintain consistent quality for Guinness Stout, but he was dealing with natural biological variation.
Barley yield, yeast cultures, temperature fluctuations.
All of it. So experiments were necessary to see if a change in process was good or bad, but they were slow, they were expensive, and they were limited in number. You might only get 5 batches of a new ingredient to test, or 8 small plots of barley.
So he's trapped by the constraints of physical agricultural reality. And the statistics of the early 20th century were, what, useless here?
Totally useless.
Right.
Classical statistics back then relied on large samples, a big N, to assume that the underlying population distribution was normal. That made the calculations straightforward.
But when N is small.
When N is small, those assumptions just break down dramatically. The old methods couldn't reliably tell Gossett if a 2% improvement he saw in a barley yield was a real improvement, or if it was just random noise from that specific small batch.
And that vacuum of certainty is usually filled by soft skills, right? By the loudest voice in the room or the highest status manager.
Which is a terrible way to run quality control. So Gossett needed a mathematical hard skill to bridge the gap between his small, noisy data and a high-stakes decision.
And due to Guinness's strict rules about trade secrets, he had to publish his findings anonymously.
Right, to avoid revealing company methods. He adopted the famous pseudonym Student, and in 1908 he published The Probable Error of a Mean. The hinge moment was his derivation of the t-distribution.
Let's define that hard skill for the listener. What exactly did the t-distribution let him do that the old methods couldn't? And why does it still matter so much today?
Okay, so the t-distribution fundamentally accounts for the added uncertainty you get from a small sample size. When your n is small, your estimate of the variability, the standard deviation, is itself kind of shaky. Gossett's distribution has heavier tails than the standard normal distribution.
What does heavier tails mean in practical terms?
It means it accurately predicts a higher chance of seeing extreme results just due to random chance when you only have, say, 5 data points.
So instead of pretending you have certainty, which the old math kind of did, the t-test forces you to be mathematically humble. It forces you to admit the variance.
Yes, it quantifies the level of risk you are taking when you act on sparse data. That is the superpower.
It's a huge shift.
Gossett gave every field that's constrained by small n, from drug trials to manufacturing line changes, the ability to act, but with their eyes wide open about the quantifiable uncertainty. It shifts the argument from, is this true, to, how certain are we that this difference is significant given our limited data?
The principle connecting Gossett and Capital One here is so vital. Small samples are not useless, they're just honest.
They're honest. They force you to be rigorously sharp with your statistical thinking and your experimental design. If you can design a clean, reliable test with only 5 data points, you can iterate at a speed that vastly outperforms a competitor who's waiting 6 months for their 5,000 user sample size.
The hard skill is designing tests that maximize the signal and minimize the noise.
That's it.
So let's detail the tactic stack for this, for rigorous experimentation.
Right.
First up, the hypothesis.
It has to be precise. You have to write hypotheses like a scientist. If we change X feature for Y segment, metric Z will improve by N%. Precision forces accountability.
Right. This feature will increase engagement is vague. It's useless.
It's useless. But this feature will increase daily active users in the Midwest segment by 3 percentage points. That's a measurable, testable lever.
And to combat our own cognitive biases, there's the rule. Build a decision rule before you see the results.
This is critical. You have to decide upfront. If the result shows a 95% confidence that Z increased by N%, we ship. If it's less, we iterate or we kill it. This stops you from rationalizing weak results after the fact, which is where the soft skills can really fail in experiment.
Okay, what about minimizing noise? That was Gossett's main challenge.
Use paired comparisons whenever you can. For example, instead of running a standard A/B test where Group A gets the old price and Group B gets the new price, which introduces a lot of noise from external factors, test a new email subject line on the same customer segment today and the old subject line on that same segment next week. By controlling for the customer segment, you reduce the noise and you get a much sharper read on the effect of the variable you changed.
And finally, and this relates back to the t-distribution, don't just focus on whether you won or lost.
Right. When the sample is small, focus on measuring the effect size, not just a win-loss. Is the 0.5% gain you saw actually large enough to justify the engineering and training costs to roll it out?
Sometimes an experiment wins, but the effect size is so small, it's not worth implementing.
Exactly. The math helps you calculate that trade-off.
That transition from argument to experiment is just pure leverage. Okay, so here's the micro-step challenge for this section.
Pick one business lever you can change this week. A pricing paragraph, an outreach script, a subject line, something simple.
Okay.
Design a simple A/B test, even if it's just 20 people versus 20 people. Track one single success metric. Write the hypothesis, write the decision rule before you run it, and then commit to the result. If the test fails to meet your predetermined threshold, you don't argue. You change the system and you run the next experiment.
Let reality be your executive decision maker. That wraps up measurement. Now let's move into section 3, engineering predictability. So we're shifting from making tactical decisions with data to designing the very structure of work itself. We're talking about the operational hard skills of flow.
And we have to begin with the master of operational flow, Taiichi Ohno, at Toyota in the post-World War II era. The context here is everything. Toyota just could not compete with Detroit's massive economies of scale.
They were facing tight capital, limited space.
High internal complexity. They couldn't outmuscle the competition. They had to outthink them.
And their core question shifted profoundly away from the Detroit model. They weren't asking, how do we produce more?
No, they were asking, how do we produce only what is needed, precisely when it is needed?
And this required a complete redefinition of what the enemy was. The traditional factory view was that the biggest enemy was idle labor. An idle worker is a waste.
Right. But Ono argued the biggest enemy was inventory.
That's so counterintuitive. Inventory seems like safety, right? It's a buffer of parts in case there's a bottleneck. How did Ono turn that idea on its head?
Inventory, Ono argued, is a mask. It's a physical mask that hides all your problems. Defects, delays, weak processes, poor communication. If you have big piles of parts between assembly steps, you can ignore that the machine upstream is broken or that the process downstream is inefficient.
Until you run out of cash.
Exactly. Inventory traps cash and hides problems. His entire goal was to expose every single problem immediately, so it had to be solved.
And the famous inspiration for his solution came from a study tour he took in the U.S. in 1956. He saw an American supermarket.
That supermarket observation was absolutely crucial for understanding pull versus push. In a supermarket, customers pull only what they want off the shelf.
Yeah.
The clerk only restocks based on what was actually taken.
So the demand pulls the supply.
Exactly, which is the opposite of the traditional manufacturing model, where production lines just push inventory forward based on forecasts, hoping someone will buy it.
And Ono adapted the supermarket style into a production control method we now know as Kanban. Let's get technical for a second. How exactly does the card system, the Kanban signal, enforce just-in-time production and limit all that inventory?
So Kanban literally just means signal or card. It's the physical mechanism that enforces the pull system. So imagine two workstations, A and B. When Station B consumes a standard container of parts from Station A, the now empty container is returned to A with a Kanban card attached.
And that card is the only authorization that Station A has to produce another container of parts.
That's it. So production at Station A is entirely dependent on real consumption at Station B. If B doesn't pull, A doesn't produce.
That's the genius of the hard skill applied to flow.
It forced every process across Toyota plants to act like this highly connected bloodstream, where demand immediately dictates supply. It dramatically reduced excess inventory, and this is the critical part, it made bottlenecks visible within minutes.
Which forced them into rapid process improvement, what they call Kaizen.
Right. By adopting this system-wide in 1963, Ono just dramatically reduced the cycle time for manufacturing a car.
And that reduction in time is exactly how Ono defines success. His quote is so sharp. All we are doing is looking at the timeline, from the moment the customer gives us an order to the point when they collect the cash. And we are reducing that timeline.
Success defined in precise, operational, hard-skill terms. His definition of success isn't about morale or engagement or vibe. It's about cycle time and cash flow.
The key principle here seems to be soft skills help you sound aligned, but operational hard skills actually change how work behaves.
Yes. Learn to design flow. Leverage comes from moving work to completion, not from simply being busy.
Okay, let's pivot to the second case study in this section. It reinforces the power of system design, but focuses on standardization. McDonald's and the speedy service system.
This is a perfect counterpoint to the complexity of the Toyota supply chain. It shows that even simple service work benefits from engineering rigor. In 1948, Dick and Mac McDonald were running a pretty chaotic drive-in. They had all the standard problems.
Slow service, inconsistent food quality, high turnover.
Soaring labor costs, because they relied on these highly skilled, temperamental counter staff and cooks.
And they chose to abandon the soft fix, which is, let's try to hire better people.
And instead, they chose the hard path. They redesigned the system so that ordinary workers performing repetitive, standardized tasks could produce extraordinary consistency and speed.
They actually applied time and motion studies to the kitchen.
They did. They narrowed the menu aggressively, focusing almost entirely on the 15-cent hamburger, fries, and shakes. And they organized the kitchen like an assembly line. Specialization of tasks, a flow-based layout, mechanized dispensers pre-assembly.
So their big breakthrough wasn't the hamburger itself.
Not at all. It was the method of producing the food at speed.
This shift meant the quality of the output relied on the system, not on the unique talent of a chef or an experienced counterworker.
And this standardization is exactly what impressed Ray Krokus, who was a salesman for milkshake mixers, when he visited in 1954.
Right. Kroc wasn't impressed by the McDonald brothers' charisma or their marketing pitch.
No. He was impressed by the sheer, predictable throughput that required them to order 8 of his milkshake mixers. He realized they hadn't just created a successful restaurant, They'd built a successful, copyable system.
Kroc realized that the hard skill, the repeatable, standardized workflow, was the foundation for Stale. He saw that the success was system-based, not talent-based, and that's why he bought in and scaled it globally.
And the principle here is so simple. Process skill helps you lead outcomes. If you want consistent results, you must standardize the steps that create them. Standardization buys you quality that's independent of a hero. It maximizes speed, it simplifies training, and it enables global scale.
But let me push back on that for a second. Doesn't this level of rigidity, especially at the level of McDonald's standardization, risk killing all local innovation? That seems to be the trade-off of this hard skill.
That's the intellectual friction we need to explore. And yes, standardization, if you take it too far, can create rigidity. But Ono and the McDonald brothers standardized the core process, the mechanism that creates value, not every single decision.
So they prioritize the consistency of the value proposition.
Exactly. The hard skill is knowing the difference between a core step that requires standardization, like the cooking time for fries, and a periphery step where a variation might be beneficial, like local sourcing for ingredients. Most organizations fail because they never achieve that baseline consistency in the core work.
Okay, so let's define the tactics for designing this kind of flow. We start with mapping.
Map the order-cash workflow on one page. Literally draw out every step, every handoff, from the moment a customer requests something to the moment you receive payment. Then go back and mark every single place where work waits.
Waiting is the enemy.
Waiting is a sign of poor flow design. It traps valuable lead time, and it traps your cash.
Next, adopting that Toyota constraint mentality. Put a hard cap on work in progress, WIP.
Yes. Whether you're coding, writing, or fulfilling orders, define the maximum number of items that can be in motion at the same time. If you hit that cap, you stop starting new tasks,
You force the team to swarm and complete existing work.
which directly improves your cycle time Ono's definition of success. And you enforce the pull signal. You only start new tasks or replenish materials based on real consumption, not on vague forecasts.
And from the McDonald's lesson, we get the checklist principle.
Turn craft into a checklist. If a task requires intuition or experience, it just means the steps aren't documented well enough. Standardization reduces variation, it increases quality, and it lowers error rates by externalizing the complexity.
And finally,
Time and motion one process. Pick one repeated internal workflow, observe it from end to end, and ruthlessly cut the top 3 sources of delay. I guarantee they will almost always be handoffs, approval steps, or waiting for a downstream system.
and for the micro-step challenge for this section.
Pick a single repeated workflow, something like your weekly reporting or client onboarding. Write down the 7 to 10 steps as a simple training guide. Then standardize just one of those steps today. Create a template, a mandatory checklist, or simple automation for that one step.
And then measure the immediate change.
Measure the immediate change in either the error rate or the time saved on that task this week. Stop managing effort, start engineering flow.
That is a profound transition. We've covered prototyping, experimenting, and system design, the whole operational side. Now we come to section 4, the master hard skill.
The one that integrates all of this.
Integrating all this operational knowledge with financial reality. We're talking about learning the numbers, which gives you conviction.
If the first 3 sections gave you operational leverage, this section gives you capital leverage. And we look at Warren Buffett's foundational insight, the ability to see the economic machine of a business clearly and quantitatively.
The story begins in Washington, D.C. in 1951 with the 20-year-old Warren Buffett. He took a train to D.C., not to network, not to meet people,
But to understand the core business fundamentals of the government employees insurance company, JGI-Co.
This wasn't a casual visit. He knew his mentor, Benjamin Graham, was involved. He gets there on a Saturday, the office is closed.
But his persistence, he ends up meeting a janitor, leads him to Lorimer Davidson, who was the second in command at the time and later became CEO. And Buffett spends hours just grilling him on the operational and financial mechanics of the business.
The insight he gained wasn't some secret tip. It was a deep understanding of the insurance business model. And to understand his next move, you have to understand the hard skill, seeing the financial machine.
Insurance can look like a boring industry, but it's a brilliant financial machine. Customers pay you premiums now, but the claims happen later.
Right.
So if the insurer can accurately price the risk, that's underwriting profit, and manage its costs efficiently, that's distribution costs, they generate profit. A key metric is the combined ratio.
What's that?
It's expenses plus losses divided by premiums. It tells you if the core business of underwriting is profitable. If that ratio is under 100%, they're making an underwriting profit before they even invest a dollar.
Okay, so that's the first layer. But the real leverage, the reason Buffett got so excited, is this quiet power of float.
Float is the sheer volume of cash the company gets to control between the moment they collect the premium and the moment they pay out the claim. Unlike traditional corporate debt, this capital is often effectively free for the company to invest as long as they don't lose money on the underwriting.
Wait, why is it free?
Because it's not a loan. It's a liability on the books, yes, but there's no interest rate. There's no immediate repayment schedule. If the insurer is disciplined and profitable on its underwriting, if that combined ratio is below 100%, the insurance operation essentially pays the company to hold and invest billions of dollars afloat.
And Buffett realized that Geico's model selling direct to customers rather than using expensive agents gave them a massive cost advantage.
Which virtually guaranteed a good combined ratio and therefore massive free investment capital.
And Buffett didn't just understand this vaguely, he achieved deep quantitative conviction about this economic machine.
And that conviction led to the definitive high-leverage action. Immediately after that meeting in 1951, Buffett put 65% of his entire net worth, which was $9,800 at the time, into Geico shares.
That is not a bet based on a hunch or a feeling or a networking tip. That is a bet based on absolute certainty derived from understanding the operational and financial fundamentals better than 99% of the market.
He could justify a concentrated position that other people would have seen as reckless.
This brings us to the core principle. Financial literacy is the master hard skill because it helps you not be fooled. When you can actually see the economic engine, the revenue quality, the margins, the unit economics, you can make decisions that create massive leverage because you understand the real risk.
As Buffett famously said, risk comes from not knowing what you are doing. Risk is often just ignorance of the math.
And in modern business, this hard skill deficit is just rampant. You see people talking about scaling without knowing their customer acquisition cost.
Or they debate strategy without knowing their contribution margin. They are, in effect, renting their decisions from consultants or VCs, rather than owning the underlying reality themselves.
If you can't do the critical calculation, you are flying blind.
The hard skill is translating every qualitative idea, like we need more features, into quantitative conviction. Like, what is the expected ROI of this feature given our contribution margin and our projected payback period?
Okay, let's give the listener the toolkit. What are the essential tactics for gaining this financial literacy?
You have to start with the framework. Learn to read the three statements. The income statement, which is profitability over a period. The balance sheet, which is assets, liabilities, and equity at a specific point in time. And the cash flow statement.
The truth serum.
The truth serum on actual cash movements, regardless of any accounting tricks.
Next, you have to make it hyper-practical and granular.
Calculate unit economics weekly. This includes your contribution margin revenue per unit minus variable costs, your customer acquisition cost, or SOC, lifetime value, LTV, and crucially, the payback period.
Let's define the payback period. Why is that specific metric a truth serum for a growth strategy?
The payback period is the time it takes for the cumulative profit, the contribution margin generated by a customer, to cover the cost of acquiring that customer. So your CAC. If your payback period is 12 months, that means you are cash flow negative on that customer for a full year.
But if it's 3 months, you're cash positive quickly.
And if you try to scale rapidly while you have a 24-month payback period, you will run out of cash and die. Doesn't matter how good your soft skills are, the payback period reveals the true sustainability of your growth.
It connects your operational costs directly to your financial survival. That's leverage.
Absolutely. You also need to build a one-page business model map. Who pays? For what? What's the pricing structure? What are the biggest variable and fixed costs? What has to be true about those numbers for you to meet your profit requirements? Externalize the engine.
The ultimate hard skill here, the one we learned from Buffett, is separating the story from the signal.
Treat every press release, every marketing narrative, every stakeholder projection as a hypothesis, and treat the core financial numbers, the combined ratio, the contribution margin, the payback period, as the only reliable test. And stay ruthlessly inside your circle of competence. If you cannot explain in detail how the business makes money and where it can break financially, you are gambling, not deciding.
The microstep challenge to close this crucial section is all about application.
Pick a company you work for, or a business unit you run, or even a public company you admire. Write the economic engine in 5 simple lines. Customer offer, price, cost to deliver profit per unit. Then today, do one calculation. Determine the contribution margin and figure out what specific operational or price change would impact that margin most significantly in the next 30 days. Find the lever.
We have just completed a deep dive into 5 essential categories of hard skills that create fundamental business leverage. This has been a study in methodology, not just motivation.
Let's synthesize the 5 pillars of hard skill leverage we've pulled from these diverse sources. First, you have the Dyson method, relentless, methodical prototyping, where reality is the only judge.
Second, the Capital One lab mentality, rigorous, large-scale experimentation that makes you correct, not just persuasive.
Third, the Gossett sharpness, knowing how to think accurately with small samples and quantify uncertainty using tools like the T-distribution.
Fourth, Ono's flow engineering, designing systems like Kanban to move work to completion fast and ruthlessly expose all the waste.
And fifth, McDonald's standardization, turning craft into a checklist, ensuring predictable quality and scale that's independent of any hero talent.
And finally, the master hard skill that ties it all together, Buffett's financial literacy.
Knowing the numbers so you can't be fooled, turning quantitative understanding into leveraged conviction.
These hard skills, at the end of the day, are not just technical tools. They really represent a fundamental shift in mindset.
Right. They substitute measurable reality and objective data for comfortable consensus and, high-status arguments.
They turn abstract goals into controlled, repeatable systems.
They equip you to act with certainty, or at least with calculated risk, while everyone else is still debating who has the best idea or the most persuasive deck. Leverage is the ability to generate superior, repeatable results with less effort because your system is just fundamentally superior.
So here's the final provocative thought for you, the listener, to mull over this week. If you can't do the math, whether it's the physical iteration count, the statistical significance, the lead time, or the payback period, you don't own the decision. You rent it from someone who does. What specific hard skill will you focus on iterating and documenting this week to gain that undeniable, measurable leverage?
Start that build log. Run that small SHRP test. Map that flow. The multiplier is waiting for the solid foundation beneath it.